Welcome to CECS 228. We're going to continue our lecture on Basic Structures Part 3, which deals with sequences, summations, and recurrence relations. So we're on page 12, which deals with finite sums, and we are going to start by looking at the definition of summation. So the sum of the terms am plus 1 down to an of a sequence is written more compactly using this notation here. So this is read as the sum from I equals m, which is our starting index, to n, which is our ending index, of ai. ai, or I rather, is a dummy variable. We can think of this as the iterating variable that changes value at every iteration of I. So starting with m, then m plus 1, all the way down to n. So for instance, they're asking us to write the sum using summation notation, which expresses the sum of the first 100 terms of the sequence aj, where aj is defined to be 1 over j for j equals 1, 2, 3, and anything greater. Okay, so what we can do is we can say for j equals 1 to 100, because I do want the first 100 terms, we're going to have the sum of 1 over j. And that would just take care of the whole thing. We have a starting index, an ending index, and an expression for the variable, which depends on j, which means that it's going to change at every iteration or every term of the sum. And this means that we're going to have a 1 over 1 plus a 1 over 2 plus a 1 over 3 down to plus a 1 over 100. For example number 2, they're asking us to evaluate the sum j equals 1 to 5 of j squared. So written explicitly, this becomes a 1 squared plus a 2 squared plus 3 squared plus 4 squared plus 5 squared, which will become a 1 plus 4 plus 9 plus 16 plus 25, and that is going to give us a 55. All right, example 3 is written a little bit differently to what we are seeing in the definition. They're asking us what is the value of the sum S is in the set -1, 2, and 5 of S. So basically what this means is instead of iterating through the values of the dummy variable in increasing order, say from one starting point to an end point, we're just going to iterate through the different values of the set. So what this means is that we have the sum be the sum of -1 plus 2 plus 5. So here we're going to have a final answer of 6. And finally, for example 4, we have a double summation or a nested summation. We have two iterating variables, I and j, and we're going to focus on first summing or finding the result of the inner summation. So if I just focus on that for a moment, I have a starting point of j equals 1, an ending point of j equals 3 over ij. So when j is equal to 1, we'll have a term of I. When j is equal to 2, we'll have a term of 2i. And when j is equal to 3, we'll have a term of 3i. So altogether, this is going to give us a sum of 6i. And so what that means then, if we have the sum I equals 1 to 4 of the sum j equals 1 to 3 of ij, and we've already evaluated the inner sum, that means that we have the sum I equals 1 to 4 of 6i. So ultimately this is going to become a 6 times 1 plus a 6 times 2 plus a 6 times 3 plus a 6 times 4, and that is the last value of I that we are replacing. So what does that mean? That means that we have, it's probably easier if I factor out the 6. We have a 6 times a 1 plus 2 plus 3 plus 4, and that is going to be a 10. So 6 times 10, which is going to give us 60. So our final answer for that problem is 60. Now on page 13 we have an interesting theorem. It's the geometric sum theorem. It reads, let R be a non-zero real number, then the sum I equals 0 to n of R to the I is equal, which is, by the way, the sum of powers of R. So starting with the 0 power, which results in a 1, plus R squared plus all the way to R to the n, is always going to have a final answer of R to the n plus 1, meaning R to the ending index plus 1 minus 1 over R minus 1. That's whenever R is not equal to 1. Or it's going to add up to an n plus 1 if R is equal to 1. And they're asking us to prove this, so we're going to take a look at the proof. We'll start with the case when R is equal to 1, because that's actually pretty simple to show. If R is equal to 1, then the sum I equals 0 to n of R to the I becomes I equals 0 to n of 1 to the I. Right? So if we were to write this out in just using the sum, we would have a 1, and that would be for the case when I is equal to 0. Okay. Because we would have a 1 to the 0. Plus a 1 to the 1. Well, okay, I guess it's probably easier to write 1 to the 0. Plus a 1 squared, plus all the way down to a 1 to the n. Now, notice, all of these are going to evaluate to 1, because 1 to any power is still 1. And if we think about how many terms we are adding in the sum, we're starting at I is equal to 0, and we're ending at I is equal to n. So that is n plus 1 ones. That means that we end up with a final sum of n plus 1, because these are n plus 1 terms. Okay, so this case is proven. Let's look at the second case. That is the case when R is not equal to 1. What happens then? What I'm going to do right now is I'm actually going to define what is called a partial sum. And so the way a partial sum works is we write S sub n, and n, or in this case capital N, is going to denote the ending index of the sum. So I'm going to go from I equals 0 to capital N of R to the I, which is R to the 0 plus R to the 1 plus all the way down to R to the capital N. Okay, so I'm going to say let Sn be this expression, which is a partial sum. And what I want you to notice from this is that if I take R and I multiply it times Sn, whatever Sn might be, that means that on the right-hand side, I'm taking R and multiplying it with R to the 0 plus R to the 1 plus all the way down to R to the n. And if we distribute that, that means that we'll have an R to the 1 when we multiply the R with R to the 0. And then when I multiply with R to the 1, we'll get an R squared. And that is going to continue until we reach R to the capital N, in which case we'll get an R to the capital N plus 1. Okay, so now if we take the difference, let's take the difference of R times the partial sum Sn minus Sn, what we'll get is that we have R1 plus R2 plus all the way down to r to the n plus 1 from this first term. Okay, and then minus Sn, the original partial sum. The original partial sum is r to the 0 all the way down to r to the n. So we have minus r to the 0 plus r to the 1 plus all the way down to r to the n. So when we carry out this subtraction, r to the 1 is going to cancel out, or is going to add up or subtract out to 0, because I'll have an r to the 1 minus an r to the 1. The r to the 2 will also subtract to 0, because technically the term that's after r to the 1 here would be an r to the 2. And all of the terms in this bottom summation, in the original partial sum, are going to cancel or are going to zero out, except for r to the 0. In the first term, in the term r times s to the n, we're going to see that everything is going to cancel out up until r to the n, right? These are going to subtract to 0, but r to the n plus 1 is going to survive. That's the only term that doesn't get subtracted out. So in the end, we're going to get something like r times Sn minus Sn is equal to an r to the n plus 1, which survived from this first term, minus an r to the 0, which survived from that second term. Okay, and now since Sn potentially is a number, right, where we just don't know which one because r doesn't have a value yet, but if we were to give r some value other than 1, Sn would evaluate to something. We can think of this as just being a number, and we can factor it out to get Sn times r minus 1 is equal to r to the n plus 1 minus, I'll go ahead and replace this r to the 0 with 1. And then if you divide both sides by an r minus 1, you get that Sn is equal to r to the n plus 1 minus 1 divided by r minus 1. Okay, now what did Sn represent? Sn was this partial sum, I equals 0 to n of r to the I. So technically what we have then is the sum I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. And n is a partial sum, meaning n is whatever number, as long as it's greater than or equal to 0. This is for sum n greater than or equal to 0. So it holds true in general. It's just a dummy variable. We can replace it by whatever. So I could actually just replace it by lowercase n. So that means that the sum I equals 0 to n of r to the I is equal to r to the n plus 1 minus 1 over r minus 1, which is precisely what we wanted to show. Okay, so that marks the end of the proof then. We have shown both cases. Let's try to apply it with this next example, example 4. They want us to find the sum k equals 0 to 10 of 2 to the k. So notice this is a geometric sum. With r being 2, okay, and n being 10. So according to the theorem that we just proved, if you have sum k equals 0 to 10 of 2 to the k, that's going to be 2 to the ending index plus 1, so 2 to the 10 plus 1, minus a 1, all over r, which in this case is a 2, minus 1. So ultimately this simplifies to a 2 to the 11 minus a 1, because 2 minus 1 is just 1. And if you have your calculator handy, 2 to the 11 minus a 1 is going to be a 2047. This is much nicer than having to list out all of the terms and then add them together. This is a lot quicker, more compact, and cleaner. Okay. Now some other useful summation formulas are given on table 2. So the one that we just saw, the geometric sum, is this first equation, except this is a bit more generalized. This is considering when you possibly have a constant coefficient in front of the r to the k. So in the one that we proved, we're just considering a to be 1. And then we would get r to the n plus 1 minus 1 over r minus 1. But if you actually do have a constant in front of there, you can simply transfer that constant over to your final answer by multiplying the r to the n plus 1 by a and the 1 by a. Now, some other ones are the sum of the first n numbers. If you sum from k equals 1 to n of k, the result is always n times n plus 1 over 2. If you sum the first n squares, so if you do like 1 squared plus 2 squared plus all the way down to n squared, the result is going to be n times n plus 1 plus 2n plus 1 divided by 6. So this one would have been useful when we were considering this example here, example 2, because that follows the sum with n being 5. Right, so we could verify that the formula will work for that. We also have a formula for k equals 1 to n of k cubed, and some for infinite sums as well, which are called series. These we'll consider a little bit later. For now, let's look at example number 5 and try to use one of these formulas to help us evaluate the sum k equals 1 to 100 of k squared. So again, this is like the third formula with the n being 100, and yeah, that's pretty much it. So we have sum k equals 1 to 100 of k squared, which according to our formula should be n, which is 100, times n plus 1, that would be 101. Plus 2n, that would be 200 plus 1, so 201 divided by 6. And so what we're going to get out of that is the following: 100 times 101 times 201 is equal to that number. That's 2,030,100 divided by 6. It's going to give us 338,350. Alright, example number 6 looks very similar to example 5. They want us to calculate the sum k equals 50 to 100 of k squared. So we have the same ending index, we have the same argument, k squared, but we don't have the same starting index. And these formulas, these have to be applied only when you have the same starting index. If you don't have the same starting index, then you can't directly apply them. You have to find a way so that they are written in the form starting at 1, going out to some other integer n. So what I want you to notice is the following. Notice that if you take the sum from 1 to 100 of k squared, that is equal to the sum of k equals 1 to 49 of k squared plus the sum k equals 50 to 100 of k squared. All right. So basically what we're doing is we're breaking up the sum of the first 100 numbers into the sum of the first 49 plus the sum of the last 51. Okay. And now, if you notice, this is what we're looking for. We're looking for the sum from 50 to 100. I can solve for this sum by subtracting the sum 1 to 49 from both sides of the equation, and we'll get the sum k equals 50 to 100 of k squared is equal to the sum k equals 1 to 100 of k squared minus the sum k equals 1 to 49 of k squared. Okay. So what's the benefit of writing it in this form? Well, the benefit is that we now have the starting index that's necessary for us to be able to apply this formula. So applying it here, we've already done it actually. We got a number of 338,350. For this number, we just have to apply the formula one more time, but now the n is 49 instead of 100. So we're going to get, this is minus a 49 times a 50 times a, let's see, a 49 times a 2, that's a 98, plus a 1, that's a 99, divided by 6. Okay, so let's give it a try. We have 338,350 minus a 49 times 50 times 99 divided by 6. So we get an answer of 297,925. We're not going to be talking about infinite sums, which are actually called series. But in order to be able to discuss whether or not a sum with infinite terms amounts to a finite number, we need to talk about the limit of a sequence. And so here's the definition. A sequence a sub n is said to converge to a limit L, and we write limit as n tends to infinity of a sub n is L, or simply just a sub n tends to L. If for every epsilon greater than 0, there is some number m such that a sub n minus L, the distance between them, is less than epsilon for all n greater than m. If no limit exists, we say that a sub n diverges. Okay, so this is actually a quite heavy definition, and I want to illustrate it by means of this diagram, what this is referring to. So if you take a look, the horizontal axis here is representing n, okay, so it's kind of like the input, and then the vertical axis is representing a sub n, meaning the term in the sequence. And so at a1, for instance, at n equals 1, we get a first term a sub 1 that is up here somewhere. If we were actually labeling these as 1, 2, this would be at 5. Okay, we would have an a sub 1 of 5. And what we're taking a look at is that when we plot all of the values, or the first few values, I should say, of the sequence, it seems like the values are getting closer and closer to some value here, which I'm going to call L. Okay, they seem to be getting closer and closer to L. And so if we want to rigorously prove that that is the case, that as n increases to infinity, this has a limit of L, we would want to consider the distance between a general an and that limit L, and say that for any epsilon that you can think of, for any distance, let's say like if I think about 0.5, that I can find a number, we'll call it m, such that after m, all of the a sub i's, all of the terms a sub I, are going to have a distance that is zero point 0.5 or less away from this limit L. Okay, this is what that is saying. This is saying the distance from the limit. Okay, a sub n minus L is the distance from the limit, will be less than epsilon for any n greater than m. So if we're starting at n values greater than m, we start seeing distances that get smaller and smaller between the ith element and the limit. Okay, so that's what that is saying. And we'll illustrate it even further with this example. They're asking us to consider the sequence 1 over n, beginning at n equals 1 to infinity. Does the limit of the sequence exist? Okay, so the first guess that I'm going to take is that if you just consider larger and larger values of n, as n gets larger, this gets smaller. And the larger it gets, the closer and closer this becomes to 0. Like if I plug in a 1 over 100, I'm going to get a 0.001. And if I do 1 over 1000, then I'm going to have an extra 0 in the 10th place, right? The number of decimal places will increase, so it'll get closer and closer to 0. So my guess is that the limit as n tends to infinity of 1 over n is 0. But now we have to rigorously prove it. So to rigorously prove it, let's just consider some arbitrary epsilon value. Okay, so consider some arbitrary epsilon value, which I'll call epsilon star, greater than 0. Okay. And what happens when we consider the distance between a sub n and the limit L? Okay, so in this case, we're saying that the limit is 0. Okay, so if we consider the distance a sub n minus 0 is less than epsilon, okay, if we want to have a distance of epsilon or less, I guess strictly less in this case, then what we can say is, well, in my case, we're going to get that 1 over n minus 0 is less than epsilon, which means that absolute value of 1 over n will be less than epsilon star. And n is only positive values, right? It's 1 or greater, so absolute value is simply just going to be 1 over n is less than epsilon star. If we solve for n, that means multiply both sides by n and then divide by epsilon star, we're going to get that it's 1 over n, 1 over epsilon star has to be less than n. And so what this is saying is that if you pick any n value that is larger than 1 over epsilon, then you're guaranteed that the distance between 1 over n and 0 will be less than epsilon star. Okay, so choose m equals, we'll take the ceiling of 1 over epsilon star just to make sure that it is larger than this ratio. So choose m to be the ceiling, then 1 over n minus 0 will be less than epsilon star for every n greater than m. Now, epsilon star was arbitrary here, so in general, if you just have epsilon, all you have to do is choose an integer m that is the ceiling of 1 over epsilon. And for any n value that is larger than that m, you're going to get a distance that is smaller than your desired epsilon. Okay, so now that we have an idea of what is the limit of a sequence, we're going to define what is the limit of an infinite sum. So an infinite series, which is defined as n is 1 to infinity of a sub n, the starting index can definitely change, but here we're just kind of adopting the convention that it starts at 1. So it's going to converge to limit L if the limit as n tends to infinity of S sub n is equal to L, where S sub n defines a partial sum beginning at 1 and ending at capital N, similar to what we saw in the proof. Okay, so let's use that definition to evaluate the sum n equals 0 to infinity of x to the n. So according to the definition, this is going to converge if the limit as n tends to infinity of the partial sum, so of n equals 0 to capital N of x to the n, converges. Now, what is this going to sum to? Well, notice they tell us that the absolute value of x is less than 1, so it's not 1, and we can actually try to use one of our special formulas here to help us out, because we have seen something raised to the m power, powers of r being summed together. And that is actually a geometric sum, which means that we're going to have the limit as n tends to infinity of x to the n plus 1 minus a 1 all over an x minus 1. Okay, so what then? Okay, well now this is where this becomes important. If it's not equal to 1, but the absolute value is less than 1, think about what will happen if you take a fraction, let's say a positive fraction, and you raise it to higher and higher powers. Like if you have a 1/2 and you raise it to the 100, what is that going to do to the overall value? Well, the overall value is going to get smaller and smaller, right? Because you keep having a larger and larger denominator. So just to write this a little bit more clearly, this is the only term that depends on n. So the whole fraction becomes the limit as n tends to infinity of x to the n minus, plus 1 minus a 1 divided by an x minus 1. And this is going to tend to 0. Okay, that tends to 0. So we get 0 minus 1 all over an x minus 1, which means we end up with a negative 1 over an x minus 1. And if we bring this to negative to the denominator and distribute, we'll have a 1 over 1 minus x. Okay, so the final sum, or the final answer, becomes the sum n equals 0 to infinity of x to the n is going to be a 1 over 1 minus x, which is actually pretty remarkable to think that if you take an infinite number of terms and you add them together, that it could sum up to something finite. But that is the answer. So with our knowledge of recurrence relations and summations, we can now put them both together to help us solve problems like the one that we saw before we talked about recurrence relations, which dealt with a person depositing money into a savings account and letting it accrue interest, but then additionally making some type of deposit at the end of the year. Okay, so example 8 reads, a person deposits $1,000 in an account that yields 9% interest compounded annually. At the beginning of each year, she deposits $500 from the tax return check that she receives. Set up a recurrence relation for the amount in the account after n years. So the first part, we're just kind of defining the rule. And so we're going to let A sub n denote how much is in the bank after the nth year. And so that's going to depend on what was in the account the previous year, plus how much interest accrued, which they tell us is 9%, so that's 0.09 times the previous year, plus the $500 that she deposits at the beginning of the year. And so writing this a little bit more compactly and combining the like terms, we're going to get a 1.09 times a sub n minus 1 plus 500. That's the recursive step. The initial value, A0, is how much money was initially deposited, so at year 0 at the beginning, and that is $1,000. So together, these two make up our recurrence relation. Okay, so for part B, we have to find an explicit formula for the amount in the account after n years. So we want to find what we've earlier called a closed formula, something that only depends on n, not that it depends on previous terms. So for this, we can use either a forward substitution or backward substitution method. We can go ahead and try a forward substitution. So A1 is going to be 1.09 times A0 plus 500. A2 is going to be a 1.09 A1 plus 500, but we are going to plug in this expression that we got for A1 into here. And that's going to give us a 1.09 times 1.09 A0 plus 500. And then bring over the plus 500. So that it becomes 1.09 squared A0 plus 1.09 times 500 plus 500. Okay, now A3. A3 will be 1.09 A2 plus 500. Simply from the recursive definition, replace this with the 3 and this with the 3. So 3 minus 1 is 2, and then plus the 500, and you'll get this expression. But then what we'll do is take the final outcome of A2 and replace it into the expression for A3, and that'll give us 1.09 times 1.09 squared A0 plus 1.09 times 500, and then plus 500, and then don't forget to bring over the plus 500 from this term. Okay, so then we distribute again. We get 1.09 cubed A0 plus 1.09 squared times 500 plus 1.09 times 500 plus a 500. Okay, so if we had to take a guess as to what's going to happen at the nth step, it looks like we're having 1.09 to the n times A0 plus 1.09 to the n minus 1 times 500 plus 1.09 to the n minus 2 times 500 plus all the way down to 1.09 to the 0 times 500. And this is a 1. Let me just rewrite it a little bit more nicely. There we go. In fact, this formula actually works, but I'll leave the verification to you. When you have some free time, just make sure you plug this back into this recursive definition and see that it holds. What I'm going to do here is try to simplify this as much as possible now that we have knowledge of summations and of some of the formulas. So the 1.09 to the n times a0 cannot be simplified, but these last terms all have in common a factor of 500. So I'm actually going to factor it out to get 500 times 1.09 to the n minus 1 plus 1.09 to the n minus 2 plus all the way down to 1.09 to the 0. And if we write it as a sum, this becomes 1.09 to the n a0 plus 500 times the sum I equals 0 to n minus 1 of 1.09 raised to the, actually let me use k so that it looks a little more, so that it's easier to read. Okay. So from k equals 0 to n minus 1 of 1.09 to the k. Now if you recall, this is again a geometric sum. So if we apply the formula, this is going to become 1.09 to the n a0 plus 500 times, the formula says take your r, which is 1.09 in our case, and raise it to the ending index plus 1. So that would be to an n minus 1 plus 1, which is just n, minus 1 divided by r, which is 1.09 minus 1. And again, that is taking it from this theorem that we proved. Okay, let's see, let's put it side by side. We just have starting index of 0, r is 1.09, ending index is n minus 1. So then the result will be a 1.09 raised to the n plus 1. In our case, the ending index is n minus 1, so it'll be just to n. Minus 1 over r, which is 1.09 minus 1. Okay, and that we can still simplify a little bit, because 1.09 minus a 1, that's a, well, just 0.09. So we have 1.09 to the n, a 0 plus a 500. I'm going to write this as a 500 over a 0.09 times 1.09 to the n minus 1. And notice this term and this term are like terms. So I'm going to try to combine them together. And just so that it writes out a little bit cleaner, I'm going to let this be represented so that it's a constant. I'm just going to call it maybe like constant, let's say like beta. Okay, so we're going to just let beta be 500 over 0.09. Then this expression becomes 1.09 to the n, a0, plus beta times 1.09 to the n minus 1. Distribute the beta, we get 1.09 to the n, a0, plus 1.09 to the n times beta minus beta. And these are like terms. We can factor out the 1.09 to the n. We're going to end up with a0 plus beta and then minus beta. So all together, we now have a sub n explicit in terms of n. A sub n is going to be 1.09 to the n times A0, which is 1000, plus beta, which is 500 over 0.09, minus beta, which is 500 over 0.09. And that would be the final answer for part B. That's our explicit formula. Okay. Part C. Part C, how much money will the account contain after 100 years? So that means they're asking for A of 100. After 100 years, well, this is where we can use our explicit formula. This will be 1.09 to the 100 times 1000 plus 500 over 0.09 minus 500 over 0.09. So let's see what that turns out to be. We have 1.09 to the 100 multiplied with, and actually let me just surround that in parentheses, even though it should work the same, but just so that we're safe. Multiplied with 1000 plus 500 divided by 0.09 minus 500 divided by 0.09. And we get a very large number, which is approximately, let's see, this is 3, so 36,240,378.52.